Okay, good day. This is a bonus supplement for a snow day. I had a student ask me to review finding new endpoints of trig functions when we're graphing them. They were having some confusion with what's going on in the book, and I have tried to oversimplify the method that's found in the book. So my method is just a little bit different, and that's why we find endpoints. They were talking something about key points. Um, in the book and in some of the other stuff. So I just wanted to go over how my method works, and the reason that I'm doing it this way is because I am trying to keep things as simple and as consistent as possible over the 6 trig functions. So I just want to do a couple here real quick examples and not spend a whole lot of time on them. So my first example is going to be y equals sine, and then it's going to be 2x minus pi. And again, we're keeping this simple because we want to, the amplitude is just going to be the absolute value of 1, which is 1, and there is no, excuse me, vertical shift in this particular function. So we're just focusing on finding those new endpoints. Now, just a real quick idea, kind of an intuition as to why we do it the way that we're doing it. It's because on the unit circle, oops, let's get the right tool here. So here's me visualizing the unit circle. On the unit circle, it starts at 0 and it goes all the way around to 2 pi. That is one full circle around. So it starts at 0 and ends at 2 pi. And when we talk about this, a simple period of any of the trig functions, we start at 0 and the first period ends at 2 pi. If I cut this into pi and we graph just y equals sine x with 1 and negative 1, we get a graph that looks like this. All right, but these are the endpoints of this simple function. And if you think of it this way, all the transformations that we did way back in section 1 were transformation, excuse me, of simple functions. So when we go to graph this thing, we're talking about transformation of simple functions. So when we find these new endpoints, we are finding the transformations from these two regular endpoints, 0 and 2 pi. And so the way that we do that is equals to 1. The way that we do that is we take this expression right here and we set it equal to these two endpoints. So we're going to go 2x minus pi is equal to 0 because that's the starting point and the starting point of one period. And then we'll set it also, or this expression, 2x minus pi equal to the other endpoint, which is 2 pi. Now, we already know something about the period, and I kind of skipped over that, so I want to go back to it. The period of this thing is still the same method. It's 2 pi over whatever we have here in front of the variable, which is 2. So our period should be pi units long, and that's going to be an important check once we get done with this. So I'm going to add pi to both sides. I get 2x equals to pi. Divide by 2, I get x equals to pi over 2. Excuse me. I add pi to both sides, I get 2x equaling to 3 pi, and then divide by 2, and I get x equals to 3 pi over 2. Now, when I subtract 3 pi over 2 minus 1 pi over 2, I get 2 pi over 2, which is a period of just pi. So these two things are my new endpoints. So when I go to set up my graph of this thing, I start with those two new endpoints. So pi over 2, and then 3 pi over 2. And I want to do a second period here, and it has to be pi units long, but we're already talking about pi over 2 units. So pi is equal to 2 pi over 2. So if I add 2 pi over 2 to 3 pi over 2, I get 5 pi over 2. So halfway between those two. So 1 pi over 2 to 3 pi over 2, if I take a difference, well, halfway between those two, sorry, finding the midpoint. So I get 4 pi over 2 divided by 2 would just be pi. And then halfway between that is 3 pi over 4. And again, you could add them and divide by 2. And so I'm counting by pi over 4. So because the difference between these two are pi over 4. Just found those differences. So this will be 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 doesn't reduce, 6 pi over 4 reduces to 3 pi over 2, 7 pi over 4 does not reduce, 8 pi over 4 reduces to 2 pi, and then 9 pi over 4 does not reduce, and then 10 pi over 4 reduces to 5 pi over 2. So just starting off and going from 1 to -1, and now we're just plugging back in to that original function, y equals the sine of 2x minus pi. I think that's what I had. Yeah. All right. So I want to plug in one number and show you how it works, and then I probably will just do the rest of these by hand. But when I want to plug in pi over 2 to see where that goes to, it's y equals the sine of 2 times pi over 2 minus pi. All right, y equals, let's see here, 2 times pi over 2 would be pi, sine of pi minus pi, y equals the sine of 0, which is our first value on the curve and the first value on the unit circle. So that's good. We know that the sine of 0 is 0, so we can plug that value in there. And we do basically the same thing with 3 pi over 4. 3 pi over 4 times 2 would be 3 pi over 2. 3 pi over 2 minus pi is just pi over 2. And the sine of pi over 2 is 1. And I've set this up right, and I'd like to do one more example fairly quickly. And I know what my pattern is going to be based on sine. So I know that that value is going to be there, this value here. And then I just connect my dots. All right, finish there. So just trying to find the endpoints here. So let's do one more like that. And so this one I'm going to do a newer one, so something that you might see in 4.6. Y equals secant of pi x minus, let's see here, pi over 2. And again, we're trying to keep this fairly simple. And secant doesn't have an amplitude, but we do know that we have there's no vertical stretch here. So that's just equal to 1. So we'll start with 1 and -1. There is no vertical shift. And I'm not doing any of that because, again, I'm trying to focus on finding those new endpoints. And my period is still going to be 2 pi divided by whatever this value is right here, so pi, giving me 2. And now my new endpoints. And just like we did in the last one, we're going to set this whole expression, this pi x minus pi over 2, equal to the endpoint 0, that's the original, and pi x minus pi over 2 equal to 2 pi, the final endpoint. And we're just going to solve for x in both of those. So I get pi x equal to positive pi over 2, and then when I divide both sides by pi, I get x equals 1/2. Now when I bring this one over, I get pi x equals to, well, I am going to add pi over 2, but 2 pi, I got to change to I have to change it so that I have a common denominator. And so I'll have pi over, or 2 pi, and I need to change that to pi, units of pi over 2. Well, there are 4 pi over 2 units in 2 pi. So 4 pi over 2. These two are congruent, or equivalent, sorry. And I have pi x equal to 5 pi divided by 2. And just like when I divide both sides by divided both sides by pi on this one. If I divide both sides by pi here, I get x equals 5/2. And again, it's important to note that 5/2 minus 1/2 is 4/2, which gives us the correct period of 2. So I feel fairly confident in that. So again, we're going to set it up, and there are no vertical shift, no fancy stuff there. So it's just, we're just going to go 1, and we're going to go -1. And we're going to start plugging in values. So there's my half, and then about here we're going to put 5/2, and then about here. Okay, so 2 is really also equal to 4/2. So 1/2 plus 4/2 is 5/2, plus 4/2 is 9/2. So now we've got 2 full periods of 2 units long. All right, so halfway between 1/2 and 5/2 would be 3/2. Halfway between 1/2 and 2/2 would be 2/2, which is just 1. And so finishing splitting everything up into quarter turn values, I'm counting by halves. 1/2, 2/2, 3/2. 4/2 is 2. 5/2 doesn't reduce. 6/2 is 3. 7/2 doesn't reduce. 8/2 is 4. And 9/2, we're at the right endpoint, x and y. And I don't think I did that on this one, so let's make sure we label correctly and not lose our points. Okay. All right, now remember, secant is 1 over the cosine of pi x minus pi/2. And so let's plug in a half. A half times pi is pi/2. Pi/2 minus pi/2 is 0. The cosine of 0 is 1. All right, at 1. 1 times pi is pi. Pi minus pi/2 is pi/2, and the cosine of pi/2 is 0, so we're going to have a vertical asymptote because we have a division by 0 there. And so again, I just wanted to, this whole section or bonus video is just talking about how to find these endpoints, and so we can clearly and fairly quickly come up with the remainder of the graph of this thing. So it's going to be every 1 unit. We're going to have a vertical asymptote. You could plug in and see these fairly easily. And go like this, go like that. Finish it up. All right, I hope this helps, and I'll see you soon. That's it.